Hello and welcome to the 10th session of Maths and Ideas. Here's Reza Negerson.
Thanks, everyone. Okay, so we ended the previous sessions with a little bit material on the most basic forms of algebraic expressions, quadratic equations. So today I'm going to talk a little bit about this proto-history of algebra, developed from Antiquity to mid-Renaissance, under the guise of arithmetic and analytical geometry. Now, so many historians of mathematics, particularly Sabbatai Orogu, the Romanian philosopher of mathematics, they believe that we can't really find anything resembling algebra in before the advent of what you might call modern algebraic expressions expressed by symbols, meaning that essentially the achievements of Babylonians, Egyptians, Chinese, Indians, Arabs, and later on people like Descartes weren't really developments in algebra, but simply pushing attempts to push arithmetics, the elementary arithmetics and geometry, to their ultimate conclusions. And we should not see these as any form of genuine algebraic developments. So the material that I'm going to present is that I'm definitely going to, regardless of this conclusion, I'm going to present a kind of material that in fact shows that even if this is really the case, nevertheless, the conceptual basis of modern algebra were developed far ahead of its advent. So, a very brief, since we are not going to overstep the boundary that we initially demarcated, which was from late antiquity to Renaissance, I'm not going to talk about what algebra is in details, but I'm going to point out a few important points about the rise of algebra, and why is that algebra is such a powerful tool, and to the extent that in modern mathematics, algebra is considered to be the king of all mathematical fields. We talk about this idea that geometry, at least in its Euclidean pre-modern manifestation, is tied to intuition and experience, at least at the level, at some a scaffolding level. you might see algebra as being the first field of mathematics that ejects the experiential dimension that for so many philosophers was plaguing mathematics. And in that sense, algebra, from a modern perspective, is the reclaiming of the sovereignty of mathematical fields, as distinguished from the kind of sciences that are at some level connected to the objectivity of experiential content. But why is that this is the case? Well, there are so many reasons that I mentioned. If I want to really articulate these reasons, I will violate the boundaries that we have been demarcating so far. But very briefly, and even though this is a very rudimentary and somehow trivial point, nevertheless it has huge consequences. And this particular reason is the use of symbols, namely a form of mathematical expression in which we are capable of studying magnitudes away from the burden of imagination that has been the driving force behind Euclidean geometry. Once we are using symbols in mathematics, we are capable of, as Katarina Dutelno-Weiss says in her book, which is about the logic of formalism, is that we achieve something quite specific in what you might call the overarching cognitive sphere, and that's the capacity to wrest an expression from a particular meaning or semantic connotation. And this is really the power of symbols that ultimately leads the computational revolution, the power of formalism, that once symbols are being treated as autonomous, and all we are dealing with is the relationship between symbols without any implicit or explicit connection with a particular context or experiential content, then we are capable of extracting these relations between symbols and reapply them to different semantic contents. So there is this process that that is happening at the deepest level of algebra. This is the process of formalization, which entails a form of duality between desemantification and resemantification, in the sense that symbols are desemantified machines, in the sense that they do not have any binding relation with a particular semantic inferential, experiential content. So this is the semantified dimension of the symbols. They are purely abstract. But the pure abstraction also means that once we understand what desemantification is, we can begin to employ symbols in the service of resemantification, namely applying them to problems, to particular contexts, which from the first glance, from our intuitive glance, couldn't accommodate these applications. So desemantification and resemantification, wresting symbols, wresting mathematical expressions from particular experiential content or semantic context, allows us to reapply these symbols, these abstractions, to new contexts. And this is really the power of algebra at its base. Another power, another reason that algebra is important, and there is such a high emphasis on algebra in modern mathematics, is precisely because algebra is ultimately a science of magnitudes. We have already came across the significance of magnitudes in the field of mathematics following Borim. And the whole idea that mathematics becomes, since Borim, becomes a science of rendering intelligible qualities of nature, or any intensive quality. And insofar as quantification, the science of quantities and the science of magnitudes are related, if we are capable of forming a new field of mathematics in which the entire emphasis is being put on the discovery of new forms of magnitudes, unburdened by our experiential limits, then this is a huge move forward in the project of rendering the structure of the universe intelligible. And hence, why is that? Algebraic notations play such a fundamental role in mathematical physics. Another reason is that so far in the kind of mathematics that we have been looking at, we don't have what you might call to be an effective calculus of problems. By problems here I mean a form of understanding, addressing, and ultimately resolving unknowables, unknowns, by virtue of the data that we are given. We talked about this idea that in Euclidean system, ultimately Euclidean system is based on data, the data that you are given. In fact, the name data, the word data means the given. So we start with our given data and we construct some new conclusions. But what if these datas, these datum in the sense of the givens, are limited, but also they are constrained by different kinds of unknowns. In algebraic notation, you might talk about these unknowns in terms of x, y, z, whatever you might call them. So this whole idea that when it comes to the mathematical project, working with the data, we need to, and this is the algebraic revolution, that we need to suspend the idea that the givens, namely the data, are always unlimited, and we can employ them in whatever way we want in order to reach certain conclusions. Algebra tries to treat these givens on a different plane, basically creating a universal tool, a mathesis universalis, in order to handle the givens so as to resolve unknowns or deal with variables that from a geometrical perspective cannot be solved simply using our given data. So these are some of the reasons that algebra became popular after the Renaissance. For a good period of time, algebra completely replaced the sovereignty of geometry. But of course, in late 20th century, mathematicians started to question about this kind of a bipolar opposition between algebra and geometry, and it started to create a form of what you might call to be a compatibilist approach between geometry and algebra, in which the kind of geometry that we are thinking about is algebraic. Namely, it is, for the most part, wrested from particularities of semantic contexts and experiential content. And the kind of geometry that we are dealing with is, the kind of algebra that we are also dealing with is ultimately geometric. Namely, it has topological continuous information. And so we see that the majority of the advances that are being made in mathematics since 1960s, 1950s are within the field or in the continuity of algebraic geometry. So, let's start with a little bit of an introduction about the origin of algebra. Even talking about the origin of algebra is, I would say, is quite a precarious mission, in the sense that the origin of algebra is not coming from a specific point or location in the history of mathematics or science. You can see the first manifestations of algebraic notations in Babylonian manuscripts, in Indian manuscripts, in Chinese manuscripts. So With that said, with the understanding that the origin of algebra is quite obscure and shouldn't be seen as a specific point in time and time and history, nevertheless, I want to kind of bracket this origin to at least a more canonical, from a historian perspective, period. And this is the rise of a scholastic Islamic philosophy. Two thinkers that I would want to cover, of course, and again, this is already a bracket within a bracket, because there were so many people who contributed to what you might call to be the modern form of algebra. These two people, one is Al-Khwarizmi, who's credited as being the modern father, or at least kind of a modern grandfather of algebra, and the other one, which I think is more obscure, but nevertheless I think his contributions were even more fundamental than Al-Khwarizmi, and his name is Tabit ibn Qura, Tabit ibn Qura, or Qura. So I'm going to talk about these two Islamic figures who were credited with the advent of modern algebra, and show that how simply by investigating geometric problems, they become capable of developing a new system of mathematics. Or if not developing a new system of mathematics, at least put mathematical development, orienting it toward what you might call to be modern algebras, or more accurately, they came up with the conceptual basis of algebra. So, is there any question that you want to ask about, some particular aspects of algebra and stuff? Or, by the way, I will at the end. I will talk a little bit about, the rise of the modern algebra, not modern algebra as it stands today, but the rise of modern algebra. I'm going to talk about a little bit about Jean-Robert Agrand, particularly his the so-called Agrand-Wessels diagram, which gives algebra a completely new power. As I mentioned, algebra is also considered to be the science of magnitudes. And magnitudes can be expressed by numbers. Now, insofar as the kind of numbers systems that we have, from Antiquity to the Middle Ages are, just natural numbers, rationals, so on and so forth, we do not have something like complex numbers. And Agrand and Wessel came up with the idea of the so-called complex numbers, which are comprised of the so-called imaginary units. And that's revolutionized the field of algebra, completely wrested algebraic expressions, the science of magnitude, from this, its arithmetic roots and its geometric roots. Even though Agrand's famous essay on the invention of imaginary units and complex numbers used the method of geometry and trigonometry. So before I start, any question, if you want like more information or any observation. Jake, I can't hear you.
I turned off the wrong thing. I was just going to ask, like, what makes the square root of -1 uniquely suited to like creating another axis of numbers? Like, is it possible to construct a different kind of complex line? If that makes sense. Something else I could equal that is not resolvable.
Can you elaborate on this question? I know what you are where you are coming from, but what is exactly the question? I mean, so you are talking about basically imaginary units. The idea that's
Right.
Given the fact that, for example, like quadratic equations or cubic equations, they can't deal with negative quantities. Negative quantities or negative magnitudes are basically the sore thumbs in basically pre-modern mathematics. And there is no such a thing as you can't see any form of analysis of what negative quantities are until the time of Kant. Kant and Hegel actually started to think about what these things are. And Agrand is the person who started to think about negative quantities not as oppositions to the positives, but as their lateralities.
Okay. Is it their actualities?
Okay, I will talk about this. What are magnitudes? What is the definition of magnitudes? Does anyone know what magnitude? I mean, the most basic philosophical definition of magnitudes. What are magnitudes?
Differences in quantity?
Quantities are being expressed in terms of magnitudes. No, quantities are being expressed in terms of magnitudes, not the other way around.
Part of me wants to use the word scale, though I can't put it into a definition. I'm thinking of scale and scalar in terms of magnitudes as opposed to directions, but I haven't got a definition.
Magnitudes, actually, it's really quite interesting that Agrand had, in his famous essay, there is this thought experiment, which of course is quite a Kantian idea, that he tries to express magnitude in terms of a scale. By a scale, I do not mean a scale like levels, but really a scale. An instrument for balance and counterbalance. Now, the thing is that Grossman apparently has given the most concise, Hermann Grossman, who was a mathematician, who is now being regarded as criminally undervalued mathematician of 18th century. And his contributions are vastly being reinvestigated. He gives a very brief definition of magnitudes, which has become the most canonical definition in mathematics. Simply, two things that can be said to be equal or not equal in one and the same subject. Now, Kant, in fact, has something also like this in mind when he tries to define negative magnitudes. He makes that famous example of a ship sailing on the ocean, being driven forward by two wind currents. The idea is that negative magnitudes are not simply opposite of the posited or positive magnitudes. positive quantities. Like the -1 is not simply opposite of +2. They are in fact both positive, or more accurately, positive quantities, completely real. It's the idea that how they join together in one and the same subject that make one a negative magnitude and the other one a positive magnitude. So a ship that, for example, being moved forward by a wind current coming from southeast and another wind current coming from northwest. Now you can see that the amount of distance that this ship has been traversed since time t1 is being determined by the opposition of these two positive wind currents in one subject, namely the ship. The directionality, the product of this opposition, is what might you call a negative magnitude or a lateral opposition.
Significance then of the square root of -1. It's something like that operation will always produce like an interminable dialectic of ones, or something along those lines.
Absolutely, this is absolutely the case. The whole idea is that, you know, the invention of zero is a machine in the sense that it is not nothing. It is simply a hinge between magnitudes. This is really the algebraic notation of zero. And why is that algebra couldn't be invented without zero? It's a hinge between magnitudes. It expresses how magnitudes balance and counterbalance one another in what you might call to be an interminable dialectics between weights, between magnitudes on different sides.
Right, like zero is in zero.
Yes. From an arithmetic perspective, which was dominant, you know, from Antiquity to end of Middle Ages, negative quantities were considered to be simply inferior to positive numbers, just because they come under it. You know, -1 is under +1, so it's inferior. They weren't even, sometimes they weren't even considered to be real numbers, precisely because of this metaphysical inferiority. But the idea, the systematic understanding of zero in algebra allowed mathematicians to think that it's really not about opposition, simple opposition. It's about how different positive magnitudes come together, influence one another, this dialectic of balance and disbalance within one single device, zero. So Agrand's diagram of complex number, or so-called Agrand vessel diagram, is that so the axis x represents real number, and it goes from plus whatever to plus whatever, and then you have, of course, the oppositional vector of it, the canonical opposition, which goes on the minus, basically, direction. But negative quantities that are being defined in terms of -i, imaginary number, or imaginary unit, are not really in opposition to the vector x, to the axis x. It's the axis y. It's a vertical axis.
I think that's what always confused me. Is it just seemed is exactly that sort of geometric z-axis, and with respect to the real line, what's the difference between like a y and a z-axis? Because you're always like having something that creates a plane with the number line like at a certain operational point, and I just didn't understand like what the fundamental significance of the square root of -1 was. But this like totally answers that.
I mean, this is how it goes. Well, for those of you who have
I was gonna add one thing real quick.
sure.
It's the whole thing with imaginary numbers, which makes it convenient for forming another axis, is the whole fact that it's a square root, and with the complex with the complex graph, it multiplying something by I causes it to rotate around.
Yes, absolutely. This is what I meant by the power of laterality rather than the power of opposition. It's and this is already manifest in Kant's example of how he defines a negative quantity, in the sense that the amount or the distance traversed by the ship is really a vector that's and this is the whole idea of vectorial analysis put forward by Grassmann, that it is no longer simply back and forth opposition like a pendulum, but it denotes a form of orientation or rotation. And a great example of this rotation, literally a rotation, is not in Agrand or Wessel, it's in Hamilton's idea of quaternions.
Yeah, I mean, I was thinking that the negative can mean, and often means, a change of direction, as in vectors, or even on the real line where you're moving left or moving right, or rotation when you introduce the square in complex numbers. I was going to say, could you elaborate a little about quaternions? I don't know if everybody, non-mathematicians, understand what they are.
Okay, actually, quaternions is a really difficult concept, and I mean, I think the best thing is that I will send you a link that there are some really good articles about quaternions and trying to make them intuitive. But for now, imagine I will give you a mechanical example of what a quaternion is. Does any of you know anything about a gimbal? It's a device being used in a gyroscope that allows you to, so you have X, Y, Z coordinates. Now, you can, which of course yields a Cartesian coordinates. Now, quaternion is a form of number on this, the product of X, Y, Z axis that allow you to see the so-called plotting or coordination. It's a form of number that you can't simply achieve it by connecting X, Y, Z of the axis and yield a specific number. But it's a form of number in which every time that you are moving from one number to another in the process of succession, you have to rotate X, Y, Z. Exactly like the kind of a 3D vector that you get in your software, and how you have to plot and you have to rotate the gimbal. It's exactly like that. And it has a specific pattern, which is rotating a spiraling pattern. So it goes like this. This is the, this is 1, this is -1. Let me share the screen. So this is a complex number. A is a real number, B is called the imaginary component, and I, which of course is a real number again, and I is called imaginary unit. An imaginary unit is that you can think of this, -1, that even under power or radicals, you get -1. This is basically the so-called grand Wessel plane or surface or graph, whatever you might call it, shows what a complex number is. And the idea is that, for example, if you have something like this kinds of equation, x2 plus 1 equals to 0. You can't really solve this equation. Basically, you can't find an answer for this in natural numbers or real numbers or any other numbers other than complex numbers, which they use basically this imaginary unit. Questions?
One thing that I thought of is it's just like how in the past negative numbers were seen as inferior numbers. I mean, it'd be important to not think of complex numbers as like inferior. It's
Oh, no, they are not by any means. And the whole idea of imaginary is just an unfortunate choice of words. Imaginary doesn't mean as opposed to real. It is actually even more real than real numbers from an ontological perspective.
Yeah.
I mean, the whole progress, it's a kind of a Russian nested doll of number systems that we have. It's naturals, integers, rationals, the reals, and the complex. And the idea is that from this point forward, we have analytical density between numbers, namely within natural numbers, between 1 and 2, you can't find any other number. But from Q, Z, R, C, integers, rationals, reals, and complex, the idea of analytical density means that you can find infinite amounts of numbers between any two numbers.
Does that apply to integers, though?
Sorry?
If it's between any two numbers, what about integers?
Oh, sorry. No, you are completely right. This is. One second. Let me. This should be. This is the box. 9 Queen Zulu ruled over. I forgot the C. This is basically if you want to memorize the sequence.
No, isn't the sequence, shouldn't it be NZQRC?
And no, I think it's NQZ. 9 Zulu Queens, or let me see. So we have naturals, we have integers, we have
Zahlen, and then rationals are Q.
Rationals are Q, yes. So it should be 9 Zulu queens, yes. Basically, complex numbers, as you see, what they differ from every other number is really because of the so-called imaginary units. Basically, we are dealing with a new axis between the negatives and positives.
And so based on that, if we were just trying to like compactly say what the complex numbers add relative to the reals, it's that we can find with the reals like planes or three spaces or whatever, we can describe rotations using a set of numbers, because we have like the imaginary axis makes it a 4 space, and part of that space is not like actual spatial rotation in the 3 space under discussion, but like things that are out of phase or whatever that are rotations, and we can describe the rotational properties in the real.
Yes, yeah, and although I wouldn't go so much as saying that it's a real 3 space, yes, but yeah, absolutely, yeah. And then, as I mentioned, I will put this link to Hamilton's quaternions, so you can see how it works. And there is, in fact, this whole idea. I mean, there is, there is gimbal in any form of orientational mechanical device, from airplanes to guided missiles and stuff. And the thing is that this is really the kind of algebraic structure that allow, for example, a projectile to change its orientation along the geodesic curvature. And quaternions are basically this idea of rotation, that they can capture Cartesian. They're not simply reduced Cartesian coordinates, but they have something else. They have this rotational axis that is expressed by an imaginary number. So, should we have a very, very brief break before I start Khwarazmi and Ibn Quran?
Sure, 5 minutes.
Yeah, sure, excellent.
Type those names into the sidebar.
Sorry?
Can you type those names into the sidebar, please?
Oh, Khwarazmi. And the other one is I think these are, I'm not sure about, because these are, Arabic names. So might not be the canonical Latinized form. Oops, sorry, that wasn't the one I wanted to.
No problem.
There is, I mean, the first application of quaternions, interestingly enough, was used in invention of modern telescopes. Because you see, the idea is that, you know, imagine that you have a telescope and you have electrical current that is, you know, you have employed a switch for turning off and on. And this on and off corresponds to quantities, you know, 0 and 1. Now you need to have a negative quantity, and this negative quantity is basically responsible to not just two coordinates moving left and right of your telescope, but also be capable of rotating it according to left and right, zooming in and zooming out of the telescope. Quaternions were used in a way of solve this problem. Basically, moving the telescope not only along the, you know, canonical Cartesian coordinates, but also giving it rotation according to its coordinates. Should we start?
Yeah, let's go ahead and continue.
Okay, so very briefly, you know, Khwarazmi's main contribution to algebra or proto-algebra is this famous book, Algebra and Al-Muqabala. which roughly translates to complementation and reduction. Algebra means to add or to complement, and al-muqabala means to reduce, suggesting two methods of complementation and reduction for solving algebraic notations, algebraic expressions and equations. By solving, I mean that these two, what Khwarazmi takes to be universal methods, can be applied to the most complex forms of algebraic notations, at least complex in its own time, and they are capable of reducing the complexity of this mathematical or algebraic notation to a simpler notation that can be solved using existing methods of its time. So, as I said, the meaning of jabr and algebra is coming the word jabr. Jabr is just like if you're Arabic or Farsi speaker, jabr is the word for algebra. There is no word. I mean, the algebra and doesn't take into account the idea of reduction. So, which is another important method of algebraic solutions. It's kind of like, so the word algebra is not by any means the totality of the algebraic method. It's simply a convenient, westernized word that has been used by the scholastic philosophers, Western scholastic philosophers of Middle Ages, to refer to the overall methods of Al-Khwarazmi. The meaning of the word jabr in Khwarazmi's mathematical treatise is adding equal terms to both sides of an equation in order to eliminate negative terms, reducing the complexity of it. Another less frequent meaning of the word jabr is multiplying both sides of an equation by one and the same number in order to eliminate fractions. Because we know that, I'm sure that some of your stuff we were looking at in the early sessions, they had fractions. Fractions are nuisances in mathematics, particularly given that the tools of the scholastic philosophers or a mathematician of antiquity, fractions are considered to be inferior forms. They're pests in mathematics of that time. So you have to come up with a form of simplifying fractions, simplifying proportions, bringing them from philosophical perspective of Middle Ages into perfection, the actual number, the 1, 2, 3, so on and so forth, natural numbers. And so jabr also means multiplying sides of an equation by one and the same number in order to eliminate fractions. So for example, if you have 1 over 13, multiply it by 13, and then you get 1. In Jabr, Al-Jabr wal-Muqabala, al-Khwarizmi's treatise, the word muqabala, let me type these. The word muqabala is...
The name to the whole book, because I was reading about it.
Sorry?
I pasted the name for the whole book because I was looking at it.
Uh-huh. I think that there is a good translation of algebra al-muqabala, I think by this guy called George Saliba. Probably it's hard to find translation, but if you want to look into it, you might be able to find it on Internet Archive, where they post, kind of old manuscripts. So nevertheless, the meaning of the word muqabala, muqabala is an Arabic word that not only means reduction, but also opposition. So basically, for example, the word muqabala can be used in terms of war, that I am implementing muqabala or against your forces. So it is reduction in terms of opposition by means of opposition, namely positing something that can oppose what has already been posited. I can reduce it and simplify it. But the canonical, the one that Khwarizmi has used in algebra al-muqabala, it means reduction of positive terms by subtracting equal amounts from both sides of an equation. There are also, within the same period of a scholastic science and philosophy, there are other Arabic or generally Muslim mathematicians who simply take the term al-muqabala to mean to equate. Namely, in the sense of comparing opposite sides. The actual meaning of the word muqabala, opposition, not reduction, opposition. The combination of the two words algebra wal muqabala is sometimes used in a more general sense. Performing algebraic operations can also just mean the science of algebra. Now, let me give you some examples of use of these words in the work of al-Khwarizmi. There is this paragraph in al-Khwarizmi. It's from page 35 of Rosen's translation of al-Khwarizmi's book. He says, I have divided 10 into two portions. I have multiplied the one of the two portions by the other. After this, I have multiplied one of the two by itself. And the product of the multiplication by itself is 4 times as much as that of one of the portions by the other. Now, it sounds like more perplexing than the Oedipian puzzle. So this is simply a literal translation of this algebraic expression. Let me turn on the again. Can you see the iPad?
Yeah.
I have divided 10 . Oh, sorry. Now, in his book, Al-Khwarizmi calls one of the portions a thing, shay, the Arabic word for thing, and the other 10 minus thing. Multiplying the two, he obtains in the translation of Rosen 10 things minus a square. For the square of the unknown thing, shay, Khwarizmi uses the word mal, which means something like wealth or property. He finally obtains the equation, a square which is equal to 40 things minus 4 squares. A square, look at the algebraic notation, a square which is equal to 40 things minus 4 squares. So the word thing in Khwarizmi's manuscript means wealth, or basically what you have. Mal in Arabic and Farsi means what you have. Wealth, thing, shay. Notice that we are not using the word unknown. That X does not represent the word unknown here. A square which is equal. So he says that, the one that I mentioned, the paragraph that I mentioned, he reduces it to simply this compact form, a square, which is equal to 40 things minus 4 squares. The algebraic expression of it is x power 2 equals to 40x minus 4x power 2. Next, he says he basically employs the method of algebra, the method of completion. Adding 4x2 to both sides, therefore obtaining, so if you add to both sides 4x2, this is the method of algebra, the method of completion. You get 5x2, so 4x2 plus 1x2, 5x2, and this was minus, so it neutralizes this. So on the other side of the equation, you have 4x, 40x, which then translates into x2, 8x. 40 divided by 5, which then leads to this. X equals to 8. So this is the implementation of the method of algebra, the method of completion. Was this clear? Okay. Now, on page 40, Khwarazmi has another equation. Which of course, again, being expressed in terms of wealth, or shay, or the things that you have. Now, he uses the method of al-muqabalah to solve this equation. As I said, al-muqabalah means to reduce in Khwarazmi, but the general meaning of it, it means that to equate by means of applying opposition. Now, using the method of al-muqabalah, this equation is this. What are we opposing to the both sides of the equation? Yes. So, in the introduction to his treatise, Khwarazmi says that Imam Ma'mun has encouraged me to compose. Imam Ma'mun is he basically was a caliph of Arabic caliph who, for the first time, he was a kind of famous patron of science and arts, but also from a political standpoint, it was extremely important because he was the first Arab caliph who started to become a patron of the Shia minority in the Muslim world. So he says that he has encouraged me to compose a short work on calculating by completion and reduction, confining it to what is easiest and most useful in arithmetic. You see, he does not use the word algebra. As I said, at this point, we do not have anything like algebra. This is not algebra really in the modern sense, but it's an algebra driven by arithmetic and geometric ambitions. In this case, arithmetic ambitions, such as men constantly require in cases of inheritance, legacies, partition, lawsuits, and trade, and in all their dealings with another, or where the measuring of lands, the digging of channels, geometrical computation, and other objects of various sorts and kinds are concerned. Now, in the first part of Khwarazmi, and this is really, he already knows the application of even the most rudimentary form of algebra, the arithmetic form of algebra. And as you see, and also as I mentioned at the beginning, insofar as we are working with many unknowns, and if we have many unknowns and only some limited givens, some limited data, how are we going to solve these problems? So you see that algebra before became kind of like a sovereign mathematical field and becoming valorized by virtue of taking mathematics away from experience, was important not because of its abstract power, but because of its applied power. And this is what, as I read the paragraph by Khwarazmi, is implying. That basically the power of this new method is in its application, where you have too many unknowns, and only a limited amount of the givens, a limited amount of data. Now, the full title of the treatise is, I was saying that in the first part of Algebra wal-Muqabalah, Khwarazmi explains the solution to 6 types of algebraic expressions, to which all linear and quadratic equations can be reduced. Let me write down these 6, which of course any advance in proto-algebra being made throughout Middle Ages can be simply seen as an extension of Al-Khwarazmi's classes of these types of solutions. One is AX2. And of course, in these types, A, B, and C should be seen as given positive numbers, or basically natural coefficients in modern lexicon. Now, Khwarazmi gives rules for solving these equations. He presents demonstrations of the rules, and he illustrates them by worked examples. In the second chapter of Algebra wal-Muqabalah, Khwarazmi is concerned with something called mensuration. This chapter consists mainly of rules for computing areas and volumes. So you see, I mentioned, if you remember, I used this word mensuration when I was talking about Urim and his idea of basically area as being the envelopment of the horizontal and the vertical, the manifestation and remission of forms. And despite all the originality of Urim, that you can see that basically he couldn't arrive at any of those revolutionary insights when he has started to think about coherently about the system of quantification, mean speed, uniform acceleration, without the contribution of people like Khwarazmi or other Arabic Muslim scholastic philosophers. For finding, for instance, the area of a circle is found by multiplying half of the diameter by half of the circumference. For finding the circumference, 3 rules are presented. If the diameter is d and the periphery p, the 3 rules are p and 7d, p equals to 10, 2, and p 6 to 8. Now, the rule 7 is due to Archimedes, who proved that P is less than 3, 1/7 times D, and more than 3, 10/71 times D. The same rule 7 is also given by another Antiquity mathematician, Hieron of Alexandria, in his Metrica, and in Hebrew treatise Mishat HaMidut, edited and translated by Solomon Gans. The rule is also found in chapter 7 of ancient Indian manuscripts, Brahmagupta. Basically, the first chapter of, and I will talk about this, but I won't go to this, basically the significance of the second chapter of Algebra al-Muqabalah. The first chapter of Algebra al-Muqabalah gives a general, basically a method of solving algebraic equations. The second one, he establishes a connection between circles, geometry of circles, and method of solving algebraic equations. Now, if you remember the previous sessions, the method that we introduced for solving quadratic equations was not using circle. It was using rectangles. And in fact, throughout the Middle Ages, particularly as being promoted by Muslim scholars, the hegemonic model of solving, the hegemonic geometric model of using algebraic equations was using rectangles. So Khwarazmi establishes a new form using circles. And in fact, any method, any algebraic equation that you can use using rectangles by simply using a new square, an additional square, and so-called excess square, or cutting a square off of it, the so-called reduction square, you should be also capable of solving the same equation that you use rectangles and the method of completing a square using circles. And this is really the gist of Khwarazmi's second chapter, which gives even more accuracy to the solving of algebraic equations. I don't go to the details of why it gives more accuracy, but you can read about the second chapter of Al-Khwarazmi's equation. There are some really good books on this. I will try to upload them. Now, back to the main scope of Khwarazmi's Algebra al-Muqabalah, which, as I mentioned, it tries to provide general but also more detailed solutions to 3 types of mixed quadratic equations. In Khwarazmi's own words, the first type reads, roots and squares equal to numbers. For instance, 1 square and 10 roots of the same amount to 39 dirhams, the Arabic money currency. That is to say, what must be the square which, when increased by 10 of its own roots, amounts to 39. The solution is you have the number of roots, divide roots by 2, which in the present instance yields 5. This you multiply by itself. The product is 25. Add this to 39. The sum is 64. Now, take the root of this, which is 8, and subtract from it half the number of the roots, which is 4. The remainder is 3. This is the root of the square you thought for. The square itself is 9. Now, in modern mathematical notation, it would be this. As I said, 1 square and 10 roots, 1 square and 10 roots of the same amount to 39 dirhams. 39 dirhams. That is to say, what must be the square which, when increased by 10, of its own roots, namely x, amounts to 39. So he says that the solution is that you should have the number of roots which in the present instance yields 5. This you multiply by itself. The product is 25. So the next step, according to this instruction, is x plus 5 to 39 plus 25 equals to 64. The sum, add this to 39, the sum is 64. Now take the root of this, which is 8, and subtract from it half the number of the roots, which is 4. The remainder is 3. So it goes like this. So the square, oh, sorry. So he gives a geometric demonstration of this. He builds a square A, B, the side of which is the desired root x. On the 4 sides of it, he constructs rectangles, each having 1/4 of 10. 1/4 of 10 or 1 or 2 as their breadth. Now the square is becomes something like this. Now the square together with the 4 rectangles is equal to 39. The ones that, you know, we're talking about 39. Now, in order to complete the square DH, the newest square that we constructed, and this is, we call it DH, we must add 4 times the square of 2, 1 over 2. The ones that we added to each side. That is 25. So the area of the largest square is 64, which we showed by algebraic notation. And its sides are 8. So if the area is 64 of this newest square, each side is 8. Hence, the side of the original square, the square AB, is 8 minus 5 equals to 3. So, as you see, within the scope of what I gave in terms of Khwarazmi's contribution, nothing is revolutionary new. All of these methods have already been introduced in Antiquity by the Greeks, by the Babylonians, by Indians, the method of completing a square. The genius of Khwarazmi is that he's capable of synthesizing them and coming up with a universal method of dealing with these kinds of mathematical problems, algebraic problems. So, any question before I move to Tabit ibn Qura? Okay. So, let me see if I've forgotten anything so far. For those of you who are a little bit confused by these rather simple but nevertheless eccentric treatments of algebraic notations, I will get back to this again, kind of like a flashback to the Babylonian time, and kind of start to build up again to our Khwarazmi and show how these are all connected. I just want to first go over like a broad scope of these two most important work in proto-algebra, and then come back and talk a little bit more in details. Now, Tabit ibn Qura is a rather obscure figure even in Muslim world, precisely because he was excommunicated. He was basically deemed as a heresiarch. So they managed to get rid of his manuscripts, burn them, and But fortunately, before his death and excommunication and burning of his books, his main manuscript and his writings on proto-algebra reached Western civilization, and they were instantly were taken up by scholastic philosophers of Middle Ages. He's also famous. Of course, there is no trace of this anymore, just the small portions of this. That after Proclus, it is famous that he gives the most incisive commentary on Euclid's geometry. So we are dealing with a person who knows Euclidean geometry through and through. And he's going to employ the Euclidean method in the most elegant way to solve quadratic equations. And from, at least from the perspective of deployment of the geometric method, is far above Khwarazmi's method, which, as I mentioned, is nothing. There is, from a methodological perspective, there is nothing revolutionary about Khwarazmi. It's a matter of how he integrates them. Because the method of completing a square, the way that we saw, is very, very similar to the Indian method that dates back to 600 BC. So, as I mentioned, precisely because his books were burned, the only version of his treatise on proto-algebra with relation to Euclid's geometry is surviving in Latin form. It's called the Domuto Octave Esper. The astronomical works, also translated as the astronomical works of Tabit ibn Qur'a. Where he gives a cosmological model of 8 spheres of fixed stars. Inside a sphere, one has to imagine 7 spheres of the moon and the sun and the 5 star planets. Now, in modern astronomy, the fixed stars are assumed to be nearly at rest and at the equinox to have a small retrograde motion with respect to the fixed stars. The precession of equinoxes, as we call them. Now, in Ptolemaic system, the equinoxes are fixed, and the stars are supposed to have a slow forward motion of 1 degree in 100 years. Now, Tabit ibn Qur'a noticed that this small amount is not confirmed by the observations. The motion of the stars with respect to the equinoxes has to be much larger. At least in the time after Ptolemy, if one accepts the very accurate observations made under the reign of Al-Ma'mun, the same caliph that I was mentioning. To explain this, Tabit assumed an oscillatory or periodic motion of the sphere of the fixed stars, the so-called trepidation. Another phenomenon which Tabit wanted to address in this manuscript was an alleged decrease of the obliquity of the ecliptic. The ancient Greeks had used a rough estimate of 24 degrees. Ptolemy had used a slightly smaller estimate due to Eratosthenes. And the observers at Baghdad Astronomical Foundation has found still a smaller obliquity, namely 23 degree by 33. Now, so within this kind of like that he had noticed observational incompatibilities within the astronomical system of his time, in the sense of the Ptolemaic system. In order to show that where these incompatibilities, these observational incompatibilities with relation to the mathematical model coming from, he started to develop his own mathematical model. And this mathematical model is what you might call to be a true proto-algebraic system. He wasn't a mathematician like Al-Khwarizmi from this perspective. He was an astronomer who sees an incompatibility between observation and the employment of the mathematical model, looks into the mathematical model, sees its insufficiency, and then goes on to develop a new mathematical system. So this new mathematical solution that Tabit develops is also called geometrical verification of the solution of quadratic equations. Or the chapter's name is on that a specific chapter where he addresses the development of this new mathematical system to address the astronomical problem is on the verification of problems of algebra by geometrical proofs. So this is a paragraph from this particular chapter. You remember the word wealth, or shay, or mal, which was the unknown in modern mathematical notation. So he says there are three fundamental forms: usul, roots or elements, to which most problems of algebra can be reduced. The first basic form is wealth, or mal, and roots are equal to numbers. The way and method of solution by the sixth proposition of Euclid's second book, as I shall describe. We make a figure, the wealth equal to the square A, B, G, D. Let me draw this for you. The wealth equals to the square A, B, G, D. A, B, G, D. We make BH equal to the same multiple of the unit in which lines are measured as is in the given number of roots. And we complete the area of DH. So first we construct this. This is, you need to look at the sixth proposition of the second book of Euclid. Yes, it's the pronunciation is mal, is like this. Shay, thing, wealth. So, and also, if you want to look at all of the stuff that I was mentioning in terms of Euclid and the homeworks, your first, the site that you want to look at is Proof Wiki. It has the best resource on the proof of all of the Euclid propositions with commentaries and stuff, quite nicely illustrated. So the first basic form is wealth, mole, and roots are equal to numbers. The way and method of solution by the sixth proposition of Euclid's second book is as I shall describe. We make this figure, the wealth, equal to the square ABGD. We make BH equal to the same multiple of the units in which lines are measured as is in the given number of roots. And we complete the area DH. Oops. Complete the area DH. Since the wealth is ABGD, the root is clearly AB. Remember, we are talking about a square and its roots. This is the area of the square, and this is its root. The root is clearly AB, and in the domain of calculation and number, it is equal to the product of AB and the units. AB and the units, in which the lines are measured. Now, a number of these units equal to the given number of roots is in BH. Hence, the product of AB and BH is equal to the roots in the domain of calculation and the number. But the product of AB and BH is the area DH. Sorry, actually, let me... Let me turn this to G and let me turn this to D so it makes sense. So he says that now a number of these units equal to the given number of roots in BH. Hence the product of AB and BH is equal to the roots in the domain of calculation and number. But the product of AB and BH is the area DH. Is the area DH, because AB is equal to BD. AB is equal, AB is equal to BD. AB, because we are talking about the square here. You need to look at the proposition 6 in the second book of Euclid. Hence, the area DH is in this way equal to the roots of the problem. Hence, the whole RGH is equal to the wealth together with the roots. Now, this explanation is, quite gnomic from the perspective of modern algebraic expression. And the reason for that, because he can't equate an area or line segment with a number. So he has to go to through the geometric method. Remember that right now We do not have any way of how to equate an area with a number. We are basically pre-Descartes time. It's Descartes who starts to associate geometry with numbers. We are still in the domain of proto-algebraic geometrical solutions, where the connection between geometry and numbers is far from obvious. Now, he therefore introduces a unit of length, which we can denote by E. If the given equation that he's talking about in this paragraph is this, 2 plus mx equals to n, in which x is an unknown number while m and n are given numbers, the data, he translated into a geometrical equations of this form. Remember, in his geometrical configuration, he introduced a unit of length, which we have here denoted by the letter E. Now, in this second geometrical equation, X and E are line segments. He then continues by saying that now the wealth and the roots together are equal to known number. So the area GH, the whole of your rectangle, is known, and it is equal to the product of AH and AB, because AB is equal to AG. AB is equal to AG because this is a square. ABGD is a square. So AG equals to AB. Hence, Tabit says that the wealth and the roots together are equal to a known number. So the area GH is known, and it is equal to the product of AH and AB, because AB is equal to AG. So the product of HA and AB is known, and the line BH, the one that we constructed, is known, because its number of units is known. To it, a line AB is added, and the product of HA and AB is known. Now, in proposition 6 of book 2 of the elements, it is proved that if the line BH that we constructed is halved at the point W, the product of HA and AB together with the square of the BW is equal to the square of AW. But the product of HA and AB is known, and the square of BW is known. So the square of AW is known. Therefore, AW is known, and if the known BW is subtracted, AB results as known, and this is the root. And if we multiply it by itself, the square ABGH, that is the wealth, is known, which is what we wanted to demonstrate. I will go through this method that Tabit uses using the second proposition of the second book next session. But you see the way that he approaches this he's still using the idea of a square, and your square is a portion of your wealth in their lexicon. It's basically your unknown. Now you either add to it or you subtract something from it. Here we added to it by constructing the line BH. And that allowed us, using the second proposition, to basically solve the algebraic equation, simply using the geometrical method. Again, I will get back to this idea of the two ways, the two more hegemonic ways of solving algebraic expressions or algebraic equations in Middle Ages, using the method of adding a square or the method of subtracting a square from your wealth, your unknowns. But of course, as I mentioned, Khwarazmi adds a different method, far more complicated, to these two ways of adding or subtracting squares, and that's using circles, particularly drawing concentric circles, which translates again to the idea of the square, but it's a more sophisticated and more general solution, geometric solution. So before I finish today's session and we come back to Tabit and a little bit more on this whole idea of the algebraic proto-algebra from Antiquity to Middle Ages, is there questions or observations?
I thought it's an interesting question. So when we were first discussing the origins of algebra, I was sort of wondering if it was something that's specifically linked to the development of the alphabet or to alphabetic cultures, because that sort of that of like a phoneme, a graphical shape, and a number for arithmetic, and certain rules for putting them together that are borrowed from spoken syntax or operation to what goes into early algebra. But like I was looking in Chinese mathematics, which never used an alphabet, and it was very sophisticated, like fairly early on. And I just wondering, do you know there being between the development of algebra or graphical rather contexts that might be explained by whether it comes from an alphabet or from a pictorial?
Well, there is this famous essay, I have forgotten, actually, I think I know, let me mention, there is this historian of science who wrote extensively, that was basically his thesis, and later he became very famous in mid-20th century. It was this Romanian guy called Sabatai Unguru, U-N-G-U-R-U, and he wrote this essay about this clash between the geometric algebra and the modern notational algebra, symbolic algebra, and he started to discuss it precisely from the perspective that you mentioned, that which I mentioned at the beginning of the session, that precisely because algebra, the whole conceptual idea of algebra is not graphical. This graphicality is not simply at the level of methodology. That's algebra, today's symbolic algebra is methodologically advanced, but it also, this change in methodology from arithmetic and geometric to symbolic, to the syntactic, desemantified version, is actually a shift in ontology of mathematics. precisely because it unburdens mathematics from experience.
Interesting. Like, I don't know if you Bernard's idea of the history of ontology organizations, reweaving space and time together symbolically.
Yeah.
Interesting to see that as well.
Yeah. Schottler has also something close to this, but not as pro-formal a stance that of Ungru. Schottler thinks that it's not that geometry loses its traction in transition from proto-algebra to modern algebra, but it is simply that once symbols are introduced, and symbols are just magnitudes, you know, they are just expressions of the mathematical relations between magnitudes that can no longer be grasped by simple geometric methods. He says that once these these symbols are introduced, namely the relations, the abstract relations between magnitudes, then you see that you are also stepping beyond the naive intuitions of a space that you have in Euclidean geometry. So rather than algebra completely divorces itself from geometry, the introduction of algebra allows for a different intuition of a space, far more advanced and complex than the one presented in Euclidean framework.
This is only.
But like, ARIM, does ARIM have algebra? Post the introduction of algebra, proto-algebra to the West.
It is post.
Post, okay.
Yeah.
Sorry, Christian, go ahead.
So this is only tangentially related, but it's very interesting. There's this speculative idea has to do with because I guess if you look at alphabets, the alphabets with vowels are always read left to right, whereas the alphabets without vowels are read right to left. I guess the idea is that right to left, like I forget like which brain is which side of your brain, but like it basically has to do with like the efficiency of how we process information. And because languages without vowels, they're more context based, and they're not as linear because you need to intuit sort of the context in which the word is found to see what the meaning is. Whereas with linear alphabetic scripts that have vowels, there's a possibility for more intense linearization and like sort of fixed symbolic abstractions.
Yes, I mean, I have heard this kinds of arguments, but as you say, they are speculative. I think this kind of argument was like particularly very popular. Is about that basically this left to right or right to left. The clash of these is the clash of what you might call to be a clash of two different systems, two scaffoldings for different potential forms of abstraction. It was put forward by Derek Kirkhope. He's a Canadian, he was a Canadian, I think he's still alive, neuroscientist and cybernetician. Theodore, it's which book are you talking about? Talking about Schottler's book?
No, was it the Unguru book that you were talking about earlier?
Oh, it's an essay. It's an essay. I have forgotten the name of that essay, but I think is something on geometrical algebra. I will find it for you. I will find it for you.
Thank you.
His name is this. I think he's Romanian. He was Romanian. And so, Onguru's thing is that it's really the power of modern algebra is its operational symbolism, and this operational symbolism allows you to identify, manipulate, and build on the relations between constituting structures. Beyond the limits of experience, beyond the limits of imagination and intuition afforded by geometrical analysis.
This is just like a really big, broad strokes question, but how, and it might not even be intelligible, how do these ontological understandings shift?
Well, the ontological understandings, I think it's not that the shift in ontological understanding, you might call it to be a symptom of shift in the paradigm of mathematical structures and operations that you discover. And this is exactly the case in the transition from proto-algebra to modern algebra, that once you start to look at operations and you start to deal with the operations in their own terms, by that in their own terms, I mean in pure abstraction, simply using syntactical symbols, then you are capable of seeing that there are a different, what you might call, level of mathematical structures that, for example, your previously posited ontological realm couldn't capture, but now nevertheless you have posited them. And then by virtue of that, you have shown that there is, in fact, a more fundamental ontological realm, or a deeper ontological realm than your previous assumed ontological dimension.
So is it through the resolving of previous contradictions in your...
Sometimes previous contradictions, and sometimes simply, as we see here, sometimes simply by abstracting mathematics more and more from a particular hegemonic current that you might call is assumed to be driving the realm of mathematics or the landscape of mathematics forward. And this is really, I mean, when you look at it, the first time that really you have something like algebra is not really in scholastic philosophy. Yes, Khwarazmi, Tabit ibn Qurra, Urim, they all have algebraic ambitions in the way that they are approaching mathematics, but simply at the level of conceptuals. The first time that you actually come up, you see that someone abstracts this idea of, for example, the relation between geometry and numbers and reinvent it on a different level, simply by a very smart form of what you might call simplification, is Descartes. This very idea that a line can be represented by two axes, bits of x and bits of y. So any thing on this graph, on this plot, can be represented by a series of numbers. That's a fundamental technological breakthrough that allows you to further abstract from the diagram, from the geometrical intuitive components. Simply because you have made explicit a new relationship between geometry, the diagram, and the number. And this is really Descartes' revolution. And without Descartes' revolution, you don't get anything of, of later revolutions in algebra or calculus. Simply identify or single out, make explicit a new relation between geometry and numbers. And we know that this relation between geometry and numbers was already the hegemonic current of the scholastic and antiquity, the arithmetic and geometric foundations of algebra. Well, once Descartes makes it explicit, he also, basically this explicitation becomes a pivot for a new form of abstraction. Although this idea that, as I mentioned, that these are just some of the more, kind of prominent characteristics of algebra and how proto-algebra turned into modern algebra. This idea of, moving toward numbers and moving towards symbolic relations, abstract symbolic relations between constituent mathematical structures. There are so many other reasons that led to the advent of modern algebra, which I haven't really seen that much historical context for them. I mean, historical analysis of these things, of these causes.
Thanks for that. So just so everyone knows, we're at 3:43 now. So if people want to do last waves of question, otherwise we can end.
Okay, I'll bite. So there's something clear about the word coefficient and the causa efficiens, out of the Aristotle's causal fourfold. Is there anyone who writes explicitly about the elementary parts of algebra, like variables, constants, operations, and so forth, in terms of the four causes? Like operations as causa formalis, variables as causa materialis, that sort of thing?
No, I haven't seen. No, I don't know if it exists. I mean, this is really interesting, but no, I haven't seen anything on this front. No.
Cool. Maybe I got a final project idea. Thanks.
Also, again, to continue that response to Theodore, the thing is that this whole idea that algebra has a deeper ontological status that, for example, geometry, needs again to be taken with a grain of salt and only be seen from the perspective of the philosophical historical reflection. The whole idea of algebra and the revolution of algebra was that it was for the first time that a mathematical field becomes impervious, indifferent the discussion about ontological status of a mathematical structure. Because you should remember, from a historical perspective, it's geometry that for the longest time has these fundamental claims about its ontological priority, precisely because it's rooted in intuitions. And algebra, using symbols, becomes impervious, that it is no longer important, really. You can take away all of these attachments, this bondage of mathematics to intuitions, and still you can have a good mathematics. For them, it's just basically at this point, you need people. People usually talk about that. Yeah, of course, for 100 years, algebra was also hegemonic to the point of ossification of field of mathematics. But you need to understand that for hundreds of years, it was geometry that was hegemonic, and it was a tyrannical hegemony of geometry. So all mathematicians wanted to do wasn't to talk about ontological precedence, but simply coming up with a way that they can do mathematics, all of the stuff that they could do with the geometric method, but no longer being committed to the philosophical ontological claims of the geometrical analysis.
So can I ask a question that I'm afraid is like idiotic? Isn't it though that mathematics is proven through empirical usage?
I think demonstrated is a better word. Empirically demonstrated. Empirically demonstrated what? What are we basically empirical usage demonstrate? The efficacy of mathematical structure in encoding the structure of physical reality. It does not really demonstrate anything about mathematics. Hence, the idea of application shouldn't be conflated with the idea of mathematical proof or demonstration. That you can, in fact, this is the whole idea that I do believe that when we are talking about the relation between mathematics and physics, and also the idea of reality, what counts as reality, what counts as being, as existence, we need to, I think, accommodate a local or global deflationary attitude. That these fields, what they mean by real, what they mean by existence, what they mean as being, need to be understood in terms of local deflationary criteria of their own fields. Mathematical entities, their reality can be proven. But the being of these entities cannot be demonstrated or verified by physics, precisely because the being of physics is different from the being of mathematics. Bunching up these forms of being together, we are already creating a bad formula for a naive realism, I think. So empirical demonstration, I think, needs to be constrained to the efficacy that all it testifies to, all it basically corroborates, is the efficacy of the mathematical structure in encoding the physical structure. It does not say anything, and it shouldn't, about the reality, the beings, or the ontology of mathematical entities as such. Because the criteria of classification of this ontology, when it comes to mathematics, is determined by mathematics as such. What it defines as being of an entity.
Thanks. That addresses parts of my question.
I kind of like that the last part of what you just said, because it kind of got into the dialogue me and you had last time. It's the illusion is seeing the effect, the practical effect of mathematics emerging merely from the material. The practical effect is almost like an import from the transcendental itself.
Yes. Yeah. I mean, if you want to be taking side with the transcendental dimension, yes, absolutely. And this is quite a Platonic thesis. This is really Plato's doctrine and how he sees the ontological status of mathematics within the realm of transcendentals. Yes, absolutely. It is always the reality doesn't come, basically the testimony to the reality of something doesn't come from what you take the reality to be, but from the transcendentals, from the ideals that you think are fictional. Okay, shall we adjourn the session?
Sounds good.
Thanks, everyone. Thanks, Theodore, for fantastic questions, and Jake and Philip and Christian. Thank you.
Thanks, Reza.
Awesome.
Thanks a lot, Reza.
Thank you very much. Okay, see you next week.
Sounds good.
Take care.